Okay, so today we're going to be looking at the NAND gate. It is a basic gate, though you don't use it in, I don't believe you use it in Digital Logic Lab. It is simply an AND gate with an inverted output. The state diagram or state table for it is the same as the AND gate, just inverted. So it's 1, 1, 1, 0. So why is this gate useful? Well, it is useful because the transistor layout for this gate looks like this. Very similar to the AND gate, just without the inverter at the end, at the output. So this takes up less space on a die chip or a chip die. So you can use this in place of a AND gate followed by an inverter, and you'll be using fewer transistors. Again, this is the simplified version. The actual implementation is a little bit more complex than that. But also, NAND gates, it doesn't have a symbol. It is A star B with a bar over it, or like that. So the NAND gate is a universal gate. Any logic function that you can come up with using and, ors, or nots can be implemented using just the NAND gate. Any function you can get, you can do with just NAND gates. So how does this work? Well, that's the inverter. Tie the two inputs together, and you have the output is inverted. So that would be this line here. If the two inputs are 0, the output will be 1. Two inputs are 1, output is 0. If the two inputs are tied together, these two are irrelevant. So you could do a AND gate by just using a NAND gate as an inverter after a NAND gate. That implements the AND gate function using NAND gates. Now a little bit more involved. We'll see how this works. The OR gate is implemented by inverting the inputs of a NAND gate. Now you can see that this works out by doing the Boolean expression for this, which is A and B bar over it all, right? That's how you would express this diagram in a Boolean expression. Now, what's the De Morgan's law? Apply it to this, and you have A bar bar B bar bar. Oops. And you switch the sign, or switch the operation, and the two bars cancel each other out, leaving A plus B. So this schematic is equivalent to the OR gate. So you have the universal gate. That all three basic gates can be implemented with the NAND gate. The other universal gate, whoops. We'll get back to this and just get back to this in just a minute. Oops. No. The other universal gate is the NOR gate. It is like the OR gate, but inverted. So the state table looks like this. Where the OR would be 1, you would have zeros. Where the OR would be 0, you would have a 1. So the transistor setup for this would be like so. A and B in the out. it is like the OR gate, but without the inverter at the output. So again, it uses, NOR gate. Yeah. Oh, I didn't change that. Negative OR gate. So it is, looking at the transistor setup, it is more simple than the OR gate. And again, it is a universal gate where you can have an inverter. A regular OR gate. And finally, the AND gate looks similar to the OR gate with NANDs. You have the inverted inputs. Feeding a NOR gate. And again, that looks like A bar plus B bar with a bar over all of it. And then by De Morgan's law, you would break the bar. And then the two bars cancel out, leaving A star B. So if you're if you only have the NOR gates or the NAND gates, you can still implement any logic function with those devices. And get what you need to be done. Let's see here. The other two gates that we are going to be looking at for this semester, there's totaling 7. The exclusive OR gate or XOR looks like an OR gate with an extra bar on the inputs. And the state table for that. is like so. It is only high on the output if the two inputs are different. Exclusively or, not and. If it was the OR gate, the AND function is included in it. This is exclusively or, either one or the other, but not both inputs are high, then the output is going to be high. If the two inputs are the same, the output is going to be low. This can be implemented in a variety of different ways. One way if the inputs are different, then one of these two AND gates will be triggered, and then the output will be triggered to be high as well. So you have inverted inputs on one inverted input on each AND gate, and then you OR them together. If either or either one or the other AND gate is high, then your output will be high. Oh, the symbol for this you'll see in data sheets. A plus with a circle around it indicates exclusive OR. It can be written out using the normal operations as being A naught B or A B naught. Now, exclusive ORs play an important role in mathematics with binary numbers. We'll get into that when we get into adders and subtractors in a few weeks. But the exclusive OR is the sixth gate that that is implemented in logic circuits. Another way to do this, a little bit less obvious, is using NAND gates. If you figure each of these three gates uses minimum of 3 transistors, and the inverters each use 1, this would be 11 transistors minimum, whereas this only has 2 for each one, and so it would use only 8. So the NAND implementation of the exclusive OR gate is more space efficient as far as putting it on a chip die. But you can follow the logic through and see where if A and B are the same, the output will be low, and if they're different, the output will be high with this implementation as well. Please stop me if I'm going too fast or anything is unclear. I realize we've used less than half an hour of the hour and 20 minutes, and I'm getting close to running out of material for the day. So there's plenty of time for asking questions and clarity. Yes.
So bottom right, that's the exclusive OR gate using the NAND universal.
Yes.
Okay, so you can use the universal for like the NAND and the and the NOR.
Yeah.
That's just like a different way to represent the same gate.
Different ways of implementing the gates. Yes. Yeah. The same configuration with NOR gates makes the exclusive NOR. We'll get that. We'll do that one next. The exclusive NOR is the last gate where you have let's see here, and or NOR. Yeah. And then this would be this would be the exclusive NOR gate. It is the opposite of the exclusive OR. The output is high when the two inputs are the same and low otherwise. This one tests for equality. It is high if the two inputs are equal. So string these together and you can have a simple circuit with that takes two binary numbers and determines if they are in fact equal numbers by comparing them bit by bit. This gate is not implemented in chips independently. You have to use either this implementation or that implementation to oops, I did a goof here. It's not an or, nor, it's an or gate. Sorry, my bad. So you have to implement it with one of these two techniques to determine equality between two incoming bits. Uh, 30 minutes to cover 4 gates. Any other details that you might want, or yeah.
So that formula,
This one right here?
like, you say very recent.
Oh, that just is the same as the exclusive NOR gate.
That's saying that's the formula for the game.
Yeah, that's the formula for the gate. Yeah. Yeah. Kind of cumbersome, but you can replace this if you're not doing algebraic manipulation. You can substitute this for that. So, yeah. Wow, I went through that pretty quick. Any other questions? I hadn't really thought about what to do for beyond this, but yeah. Some of the homework. What? Yeah, the last session we talked about this. First or second section, but we can go through this. Yeah, okay. We'll go through a couple of examples from the homework. So get a little practice with this. Let's see here. Start with doing a circuit from a equation. Sound good? Okay. Say we have A plus A prime B plus C. Okay. You're going to have A and A prime here. So your inputs are going to be like so. And you're going to have A primed. So go ahead and take care of that right off. Primes are taken care of first. In the parentheses, ands are taken care of first. And then the ors. So A prime B is going to be anded together. Then it's going to be ORed with C. And then you take the outer portion, and A is ORed with that. You see, I did that, worked from the inside out. Inside the parentheses, on the left, work your way out as you move to the right. Okay? Let's see here. A and B plus C. Something a little bit more simple. Take care of the parentheses first. B plus C is like so. And then A is ANDed with that. But you take care of the inner parentheses first, the functions inside that. The order of operations are parentheses first. Inverter second. And then ANDs. And then ORs. So that's your order of operations. And then you work through the order from left to right, input to output. Okay? Kinda?
Like, does the letters stand for a gate?
No. The letters are the inputs. The gates are the star and the plus.
Do you know which gate to put in?
Oh, because the OR gate is the plus. The AND gate is the star. So this was in the last week or so. We AND is A star B, A dot B, or just AB. And then OR is A plus B. And inverter is A prime or A bar. And you would translate this to be inversion of A, ANDed with B, and then have that ORed with C. Let me change colors here. We got the prime here, this AND here, the OR here, and the OR here. Okay. All right. Now, as far as gate reduction in Boolean algebra, we'll do a simple example. Let's see here. Let's say A plus A prime B primed. We'll put a star in there for clarity. What can you do with this? Remember De Morgan's law? When you have a function or a expression that's inverted, you can do A plus A prime prime plus B prime, and the double prime here, A plus A prime prime, the A double prime is just A plus B prime, and A plus A is A. It's just simply A. So you have just A plus B prime. So you have De Morgan's law here, and then the double negative, and then I believe that's the idempotent. A plus A is equal to A. So just simplify the expression to the minimal number of gates. In this case, you have two, the OR gate and the inverter. Okay. Let's see here. Let's see. Do another example here. Yes. Oh, idempotent. It's the law that I believe that says A plus A is equal to A, and A equals A. So, yeah. I wasn't sure how far we'd get along today, so I pushed back the due date on the homework to be next Thursday rather than this Thursday. Although I think after today you should be able to do all the homework. I'm not sure. I have to look over it again, but and make sure everything is covered in the next two sessions to make sure you can cover the homework and all that sort of thing. But want another example or of Boolean algebra, or or you think you're good? Okay. All right. Have a good day. See you all on Thursday.